Hello, I'm Jennifer Williams, and today we'll be talking about comparison of speech representations for automatic quality estimation in multi-speaker text-to-speech synthesis. It's a pleasure to talk to you today, and I also want to thank my co-authors Joanna, Pilar, and Simon King. The problem that we want to solve with this research is how to develop a neural network that will output a mean opinion score given some synthetic speech input. Some of the motivations for this work are to speed up the TTS development cycle, to save time and money for listening tests, and to predict TTS quality automatically. There have been several attempts to develop an automatic quality estimation system. P563 was developed for coding, and there is no correlation to text-to-speech. PESC was also developed for telephony speech. It requires a high-quality reference, and it is based on comparing degraded speech to natural speech. TTS errors are not always captured in this approach. AutoMoz is interesting, but it was limited to only the Google TTS systems, and the ground truth was based on multiple Moz tests conducted over a period of time. QualityNet was introduced in 2018. This was for speech enhancement, and it is limited to the TIMIT dataset. In 2019, MozNet was introduced. This is for estimating the quality of voice conversion systems. We found that the pre-trained models provided do not generalize well to text-to-speech. The main contributions of this paper are to retrain the original MozNet framework using TTS data and explore frame-based weighting in the loss function. We also train a new low-capacity CNN architecture on the TTS dataset and compare 8 different types of speech representations. Finally, we characterize Moz prediction performance based on speaker level rankings. Our approach is basically in 2 phases. In phase 1, we develop speech representations, train a Moz network, retrain the original Moz network using TTS data, and we determine what is the best representation and model for TTS. In phase 2, we train a new held out multi-speaker TTS system, conduct a small Moz listening test, and apply a trained model from phase 1 to analyze the generalization. The question that we want to answer in phase 2 is, does our best model developed in phase 1 generalize to a new TTS system? One of our main contributions is that we explore different types of speech representations. In our low capacity CNN architecture, which we developed to handle these new representations, we have 5 different types of X vectors. Now, these are just like regular X vectors. However, during training of the X vector, which I'll talk about in just a minute, the target is not necessarily speaker ID. We have one version of the X vector where the target is in fact speaker category, speaker ID. Then we have another type of X vector where the target is a categorical variable representing room size from the PA ASVspoof dataset. We have another type of X vector that is modeling categorical values for the T60 reverb time, another one that models talker to ASV distance, attacker to talker distance, and finally another one that models the device quality. We also have the deep spectrum features, which is a output of a ImageNet pre-trained model that is operating on the entire spectrogram as an image. So this is a very high dimensional representation. Finally, we have the acoustic model embeddings. And those are from an ASR system. Again, those are 512 dimensions, similar to our X vectors. Finally, there is the original MozNet, which uses frame-based features, and we're retraining that on the LA dataset. When we create these different types of environment X vectors, we have as targets, again, speakers, room size, the T60 reverb time, the distances, and the replay device quality. So the purpose is to use the X vectors to model different types of environments and attacks that are labeled in the 2019 ASVspoof physical access dataset. So we're getting labels for free from the physical access data, and we want to use those to model speech degradation that we'll then apply as a way of modeling the degradation in text-to-speech. So when we train our low-capacity CNN and the original MOSNet, we are working on the logical access data set from the ASVspoof challenge. This is the evaluation portion of the LA data set. It consists of 48 unique VCTK speakers. Importantly, there are 13 different TTS and VC systems in this data set. So we get a wide range of quality of TTS and voice conversion output, and most of the systems are in fact text-to-speech. Also importantly, as they were evaluated with human judgments and a ground truth judgment on a 1 to 10 point scale for mean opinion score, all in the same MOS rating test. So rather than like the AutoMOS, different MOS tests over time, this alleviates that problem. We used a speaker disjoint train, valid, and test split. And in table 1 of the paper that I reference here, we can see these systems are labeled A07 through A19. There's 13 of them, and they have different characteristics. So for example, they use different types of vocoders. So some will use Griffin limb, others will use a high quality neural vocoder such as WaveNet or WaveRNN. So again, we explore 2 types of MOS prediction neural networks. In the first case, we have all of the machinery that comes with the original MOSNet, which has different types of architectures. For example, there's one version that has a bidirectional LSTM, another version that has a CNN, another version that has a CNN BLSTM combination. And so with their code provided on GitHub, we get all of the architecture, and we explore all of the different hyperparameters that they explored. In addition to that original MOSNet, we introduce our low capacity CNN, which we use to operate on our different representations, such as the X vectors, the deep spectrum features, and the acoustic model embeddings. So now we're going to talk about some of the findings that we got from our experiments. First, we used 4 different correlation metrics. So each of them have different ranges and different trade-offs and might be useful for different types of problems. We wanted to keep in line with previous work, which used these. We also introduced the final one, the Kendall-Tau rank correlation. So first off, we have the linear correlation coefficient, the LCC, also known as Pearson R. It's a value that ranges between -1 and +1, depending on the correlation, +1 being highly correlated. We also have the Spearman rank correlation coefficient. One of the benefits is that it's non-parametric, and the values again range between -1 to +1. We also use mean square error, and now this is not ideal since it fails to capture the distributional information such as outliers. And finally, again, we have the Kendall-Tau rank correlation coefficient, which is useful in this task because it captures ordinal rankings, and it is a little bit more robust to error sensitivity than the Spearman rank correlation coefficient. So here is a large table of our first set of results. Now this is the correlation between the ground truth MOS scores from the LA dataset and our predicted MOS scores from our different systems. They're aggregated in 2 different ways. One is at the system level, and the other is at the speaker level. In this work, we're particularly interested in how different speakers contribute to the overall quality of a TTS system, so we'll focus our discussion on the speaker level results. From left to right, we have the different systems and the different representations. So starting with this first column, pre-trained voice conversion CNN. This is the pre-trained model that comes with the original MOSNet on GitHub. It is trained on voice conversion data, and here we have applied it to the LA dataset. And what we see is that there is almost no correlation between the pre-trained model and the TTS data. When we retrained the MOSNet, same architecture, but we retrained it on the LA dataset and then evaluated again on the held out portion of the LA dataset, we get much higher correlation. We can see that the method for MOSNet, the architecture, is fine, except for it needed to be retrained on the data. Then we have our array of different representations that we compare our set of X vectors as well as deep spectrum features and acoustic model embeddings. These were ran on our low capacity CNN, which we trained from scratch. So there's no pre-trained models in this experiment. What we find is when we consider all the different correlation metrics here at the speaker level aggregation, we identify X vector 5 to be the best representation. Recall that X vector 5 is modeling device quality, so it does make some intuitive sense. And it's worth mentioning that the retrained logical access CNN MOSNet architecture also performs quite well. So here we want to characterize some of the best and the worst TTS systems. So for example, we identified using the ground truth that system A08 is the poorest quality system. It has a mean MOS score of 1.79, and it is an HMM-based TTS system, so it makes sense that this might be the worst performing system. And then we identified the best performing system, the highest quality, having a higher mean MOS at 5.58, and that is in fact the Wave RNN TTS system. So now let's listen to some examples of what this speech sounds like. What we see here in the plot is that while the true ground truth MOS label has quite a spread between 1 and 6.5, the values being predicted by our systems are in a very narrow band. So we have this range from about 2.5 to about 3.5. So it's a very narrow band.
Dialogue is the key.
Okay, that is the Wave RNN, and here's the HMM.
Today will tell.
Let's get a little bit more buzz. So next, we also want to characterize the best and worst speakers. And here's where things get a little bit tricky. So we have the best system, which is A10, and the worst system, which is A8, like we just saw, the HMM and the WaveNet. Then we also have the best speaker and the worst speaker, which we identified. So our best speaker in the LA dataset, based on ground truth, is the speaker label 0048, and the worst being 0040. Now, when we look at what the true MOS score is, when we look at in terms of best system, worst speaker, worst system, best speaker, the true MOS score has quite a big gap. However, our predicted mean opinion score from the model is much narrower in the difference, and also the ordinal ranking is reversed. And let's listen to some examples of that.
The culture of rugby has changed dramatically in the past 5 or 6 years.
So that was the best system and the worst speaker.
Today will tell.
That is the worst system and the best speaker, and it does sound that they are somewhat close. Let's listen to it again.
The culture of rugby has changed dramatically in the past 5 or 6 years.
Today will tell.
Okay, and so the fact that we're hearing some closeness may correspond to the narrow range of scores predicted by our system. Next, importantly, we want to talk about the ad hoc analysis that we did. So how well does this MOSNet that we trained generalize to a completely held out TTS system with held out data? So for this, we have the Libre TTS data set. That is audiobook data. We have a large set of that. It's 586 hours with 2,000 speakers. Now that did undergo some cleaning from Google. And we have a small subset that we trained our TTS system on, which is 60 hours of male and female, which is 145 speakers, so balanced across the two genders. And we have approximately 37,000 utterances that we trained our TTS system on. The TTS system that we explored is DC TTS, otherwise known as Ophelia, and it's just DC TTS with one-hot speaker codes incorporated into the system. This TTS system consists of a text-to-mail network. It also has a spectrogram super resolution network, and the audio comes from Griffin Limb. So we will hear the Griffin Limb in the next slide. When we apply the MOSNet to the synthesized speech for Ophelia and aggregated the speaker level, what we do see again is that the best representation as far as correlation metrics go is X factor 5, which is the device quality, as similar to before. However, the correlation overall is quite poor. So we cannot say that the MOSNet is working very well on this data set, even though we have identified a better representation to use compared to the others. So even though the MOSNet doesn't generalize well to this new system, when we use our best performing representation, the X factor 5, what we can capture is some relative speaker rankings.
Life is obstinate and clings closest, where it is most hated.
So that would be the worst speaker synthesized from our system. Here's a mid-range speaker.
I read it half through before I broke a window.
And here's our best.
I'm here to fetch you, she answered in her frank and fearless way. Come upstairs with me.
And when we look at them side by side, so the Libre TTS and the WaveNet, so our Ophelia system and the WaveNet. So when we look at these side by side, we have the Ophelia DC TTS with the WaveNet from the LA data. What we see is that the speakers in each system contribute differently to the overall performance of the system. So there are some speakers who will just do outstanding in both systems, and some speakers that are generally much worse. Now, if we take the worst performing speaker from the Ophelia trained on Libre TTS and the worst performing speaker in the WaveNet TTS and put them side by side, let's listen to that.
Lucifer was looking at him with a different lip.
Okay, that was DC TTS, and here's WaveNet.
It is great news for the viewers and fans and for Scottish football at all levels.
Okay, so both are actually quite poor. And what we find is that by selectively choosing the speaker to evaluate the TTS system on, one could artificially lower or boost the overall system score. So selecting only the speakers who are performing very well would boost the overall system score somewhat artificially. So in conclusion, what we've determined is that the overall approach for doing MOS prediction is sound, but the correlation between true and predicted scores could be improved. The MOS prediction model, trained on the LA dataset, does not generalize well to our held out TTS system and data. And we did find that some representations are better suited for this task, and other representations are just not well suited to this task. We have made two tools available on GitHub. So the first is the MOS estimation low capacity CNN using the X factor 5 device quality X factor, and we provide a pre-trained model. The second tool is the original MOSNet architecture with a pre-trained model that is retrained on the LA dataset. So the original MOSNet provided a pre-trained model for voice conversion, and we are providing a pre-trained model for TTS. Some of the future directions are to look at predicting speaker similarity. We also think it would be interesting to use ASV and spoofing countermeasure scores to predict the MOS score. We think that it would be important to try to reformulate this task as a Mushra or A/B preference test. And finally, we would like to incorporate automatic MOS estimation into the TTS training process. Thank you very much for listening to the talk, and we hope you enjoy the paper.